Hi, Year 12. I'm recording this in school, so I apologise for any background noises. Now, with a submission question, well done to those of you who realised that the two lines crossed again up here. So, if it's easy to sort of sketch the graph and not realise there's a second intersection up here. And also, when you're working out these points, a few of you used inequalities here. I tend not to worry about inequalities. I just say, right, where do they meet? That gives me my key values. And then I've just got to work out, is it, less than that and more than that, or is it the bit in between? So my colour coding helps me there. We're asked, when is the graph I drew red below the graph I drew green? And it's red everywhere from there to there. So it's the sandwich is the answer there. Now, a few of you did it differently and got the correct answer, which is fine. I do think the graph is always a good idea. And that's perhaps best illustrated with one of the other questions I got you to look at from the last lesson. This was the one from the book where you're asked to identify the mistake the student has made. And they are sort of using the assumption that you're going to get, when you've got a modulus equals non-modulus, you'll get that equals that, and then the minus version of that equals that, and they've gone through and worked out those two key points. And there's nothing wrong with the algebra there. However, if I sketch this, and you could sketch it manually, I happen to actually use my calculator to sketch it, you actually see that there are no intersections. The graphs never meet. So you might be saying, well, how have you worked out two intersection points? Well, the intersection point here would be where those two lines meet down there, but that's nonsense because this is a modulus graph, and this intersection is where that line carries on and meets there. So the graph was essential to show that actually, whatever the algebra says, there were no intersections, and that means there were no solutions to this problem. And well done if you managed to spot that. So here's another slightly harder, perhaps modulus problem. We're given a function, and we're asked to sketch the modulus of that function, so the bounced version of that function. And then we're asked to solve an equation relating to that function. And as you know, if it had just said this, I still would have sketched the graph because I solved these by sketching. So sketching the modulus of this function here, well, you know that the best way to do it is to sketch the function itself and then bounce it. So this function here, I'm going to suggest to you that the way to do it would be to think about what 1 over x looks like. Then think about what 1 over x minus 2 looks like. So that's where I've replaced the x with x minus 2. And then think about what 3 over x minus 2 looks like, which is multiplying the whole function by 3. So that's, well, hopefully you remember what that is. And then think about what the modulus of that would look like. So just pause at this point and see if you can go through that sequence and sketch those functions, ending up with this sketch here. And of course you can always check it on your calculator. Pause and have a go. Okay, so 1 over x is a function that we're expected to understand, has asymptotes on the x and the y-axis. If I replace x with x minus 2, hopefully you remember that shifts everything a translation, sorry about that noise. That's a translation of 2 units to the right. So the y-axis asymptote is now the x equals 2 asymptote, so it looks like that. And as to, it's now got a crossing point on the axis. It's always good to work those out. So that's what you get when x is 0, which is going to be 1 over minus 2, so that's minus a half. If I then jump to 3 over x minus 2, that just stretches it up and down by a scale factor of 3. X-axis doesn't move. So actually this point here becomes 3 times as far away, so that's going to be minus 3 over 2. And then when I bounce it, when I say what's the modulus of that, well, this arm has no problems because it is already positive. But this arm here is negative, so that's going to become positive. So we're going to get this function here. So that's the function that we are being asked to consider. And the equation we're being asked to solve in the second part of that is, where does that graph equal 4. Now remember, this branch is 3 over x minus 2. The bounced branch will be this multiplied by minus 1. And we need to be careful here. If we multiply everything by minus 1 in this fraction, it's actually the same fraction. So actually the bounced bit is just minus 3 over x minus 2. We don't multiply everything by minus 1 in that case, we just multiply the numerator. So to solve this, I'm going to ask where, that's 1.5, so 4 will be up here somewhere. I'm going to get a ruler. So I've got 2 intersection points, so there'll be 2 solutions, 2 places where my modulus graph crosses the y equals 4 line. So I plotted y equals that, y equals 4, 2 intersections. Go on, just see if you can finish the question by solving those for me. Pause and have a go. So I'm regretting making my diagram quite so small, but there we go. So I've got A, I put the point I called A anyway, where the bounced portion, minus 3 over x minus 2, equals 4. Remember, when it's a fraction, just the numerator becomes negative. And then the point B, which is where the original function equals 4, and then I solved them to get the 2 points. And I've confirmed that, and it's not an inequality, so it's equals. No, we need to worry about inequalities. And I've confirmed that with my calculator, so I'm just going to use gsolve and intersection. So that's the first one, 5 over 4, 1.25, yeah. And then the second one is 2 3/4, 11 over 4, bingo. So there we go, that is that. Okay, so that's the end of modulus graphs for now. Although it will probably be worth doing a bit more practice of solving the equations, but I want to move on to the next development of this particular topic now. So where we go with this now is to talk about functions in general. So a function is where we take some input numbers, tend to call them x, we do some maths to them, including separate functions like squaring and square rooting and multiplying and modulus, and we get other values out, which we tend to call y values. The numbers that we're allowed to put into a function are referred to as the domain, and the numbers that come out of a function are referred to as the range. And you might be thinking, well, hang on a minute, why can't I just put any number I want in? Well, some functions I can. Y equals x squared, I can square any number. So the domain, x, is a member of the set of all real numbers. There's no limit on the values that I can put into that function. And the range, well, let's have a look at what the y equals x squared graph looks like. What y values do I get out of this function? Well, I never get negative values when I square, so it's always going to be greater than or equal to 0. So the range, if the function is described as y equals, we would say y is always greater than or equal to 0. Or if it had been described using f of x notation, we would say f of x is greater than or equal to 0. And a sketch, or using a calculator, is the secret to working out the range. It's nice and easy once you've done that. So the domain, the numbers I can put in, the range, numbers I can take out. Now let me get you to think about a couple of other examples then. So think about these two functions here. What are the numbers I'm allowed to put into that function? And what are the numbers that are going to come out of that function? And what about y equals e to the x? What are the numbers that I'm allowed to put into that function? And what are the numbers that are going to come out of that function? And I think particularly for the range, a sketch is the secret to working that out. Pause and have a go. Okay, so 1 over x. So 1 over x, I know what it looks like. And I can put any x value in, apart from x is 0. 1 over 0 you can't do. So we say that we tend to say this, x can be any value we want, apart from 0. Now, to be honest with you, that would be good enough. Sometimes you see that, sometimes you don't. But x can be any number you want apart from 0. And the range is the same, isn't it? We get any number, so we could get any number down to infinity and up to positive infinity, sorry, negative infinity and positive infinity for y, but you're never going to get y is 0. So the range, y is any number, but it won't be 0. E to the x, well, a little sketch of e to the x. I can put any number I want, any x value. I can do e to the power of anything I want. So, but the range, well, this graph never reaches 0, is it? So y is always going to be greater than 0. And understanding domain and range is really important. And let's think about one other key function, and that is the y is equal to the square root of x function. So the domain, well, I can't square root negative numbers. So the only numbers I'm allowed to put into that are x is always greater than or equal to 0. So it can't be any number now. It's got to be a number bigger than 0. Now the range, well, we need to remember something for this. This symbol here means the positive square root. It doesn't mean, so that symbol of 4 is not plus or minus 2, it's 2. And that's why when we do square roots, we have to write plus or minus in front of the symbol. So that symbol there just means the positive thing. So the graph of the square root of x actually looks like this. So the y values are always greater than 0 as well. You never get any negative y values out of that function. Okay, a couple more definitions. So functions fall into 3 broad categories, although actually, strictly, only 2 of the 3 are truly functions. And this is called a mapping diagram, where we say, right, okay, these are the numbers we're putting in, and these are the numbers that are coming out. So it's a little bit like a slightly more grown-up version of our function machine from primary school. So a 1-1 function is a function where for every number that you put in, there's only one number that comes out. So for example, let's just use f of x notation. There we go. So I'm not talking about domain and range now. I'm just saying for every number that you put into that function, you get exactly one number out. And those are called 1-1 functions. There are some functions where more than one x value will give you the same y value. For example, y equals x squared is an example of that, because if I put 2 in, I get 4 out. If I put minus 2 in, I also get 4 out. So that's called a many-to-one function. A many-to-one function. So there are several x values giving me the same y value. And then you get those examples where a single x value can give you more than one y value. Now we've already said that y is equal to the square root of x is not an example of that, because although the square root of 4 is plus or minus 2, that symbol only means the positive. But that function, which does mean either positive or negative, that is an example of this. So if you put a 4 into this function, you get a minus 2 or a plus 2 out. This is, by the strictest definition, not a function, but it's referred to as one-to-many. So we have 3 sorts of function, although this one is strictly not a function. This is the domain, the numbers we're allowed to put in. This is the range, the numbers that come out. 1-1 function has 1-to-1, many-to-one, several different x values can give you the same y value, and one-to-many, a particular x value may give you more than one y value. So if you have a look at page 31, question 2, or you could just look at it now on the screen, here are 6 sketches of functions, and I'd like you to decide whether they are 1-1, many-to-one, or one-to-many. Okay, so let me get it all on the screen so you can see it all in one go. And pull my focus. So go on, have a go, pause, and see if you can do that for me. Okay, so here this looks like x cubed. We don't know exactly what it is, but it's sort of x cubed. So if I go along the y-axis and sort of go up or down, for every x value, there's only ever one y value. And for every y value, there's only one x value. So this is an example of a one-to-one function, sometimes just called 1-1. This is a 1-1 function as well. Every x value only has one y value, so that's a 1-1 function as well. This function here looks a bit like the square root of x when that's written as x to the half. So I've got a particular value of x giving me more than one y value. So that is one to many. So this one here, I've got a particular value of x giving me more than one value of y, a particular value of y giving me more than one value of x. But one to many trumps many to one, so that's one to many. Here, each value of x is only giving me one y function, but values of y come from more than one x value. So there are more than one x. So for example, taking this value of y here, whatever that might be, there's more than one x value giving you that value of y. So that's a many to one. That value of x and that value of x both give you the same value of y. And lastly, we're back to a example where we've got each value of x only gives me one value of y, but each value of y comes from two values of x. So for example here, I've got two values of x giving me that same value of y. So that's another example of a many to one function. Now I find this really confusing to get my head around it. So I always start on the x-axis, and these ones here where you've got both, that's particularly tricky. But yeah, hopefully you can make some notes and sort of get that ingrained. Let's do a little bit more practice of this sort though. Okay, so here's a question that just looks at this idea of mapping diagrams and whether functions are one-to-one, but it gives you a very limited domain. So we've talked about limiting the domain of some functions so they work. So for example, 1 over x, x can't be 0. But here we've limited the domain still further. I mean, there's no reason why x can't be 7 in this function, but for some reason we are limiting the domain. And that's obviously going to affect the range, isn't it? So let's have a quick look at A. And we're asked to draw the mapping diagram, state whether it's 1-1 or many to one. So is it that or that? And then state the range. So if I put 3 into that function, I get a 12 out. If I put 4 in, I get 17 out. If I put 5 in, I get 22 out. If I get 6 in, I get 27 out. So this is a 1-1 function. And for the range, well, the range is what y values do we get? So if it wasn't for this limit to the domain, I'd say, well, I get any y value from this function. F of x can be any value. However, we're only putting those numbers in. So actually, it's just f of x can be equal to those numbers there. Simple as that. So go on, see if you can have a go at these two here. Mapping diagram, what sort of function they are, and the range. This is much easier. Normally we'd have to sketch the functions. In this case, it's just what y values do you get from those x values. Pause and have a go. So with part B, you don't have to present it like this. You could have just had -3, 6 and -3, 6, but I was just following the lead from their diagram. Both -3 and +3 give you a y value of 6 with this function here. -3 squared is +9, and 3 squared is +9. Take away 3 gives you 6. And the same for -2 and 2, both give you 1. -1 and 1 both give you -2. And 0 gives you -3. So you could have put the mapping diagram like that. So this is a many-to-one function. And the range, well, normally, the range of x squared -3, that graph would, like this. So we'd say, right, the range is that y, or in this case, g of x, can be any value greater than or equal to -3. But actually, in this case, g of x just equals 6, 1, -2 or -3. Easy peasy. And then the last function, a bit fiddly, but with those only 3 numbers that you're allowed to put in, you get a very limited range. It's a 1, 1 function. And h of x, the range h of x, is just equal to those 3 numbers there. So on page 54, question 5, it's another one of these where you just got to say, it gives you some graphs, you just got to say whether they're 1, 1, many to one, or one to many, which isn't really strictly a function. Just do part 1. Part 2 says which of these can be a function. So it's basically your answer would be which of them were that or that, because that strictly isn't a function. But I think it's an unnecessary complication. So it looks almost identical to this question we did earlier, but you've just got to say which of the 3 the pictures are. That's not a submission question, but I am going to start tomorrow's video by going through that. So I think it's helpful if you've done that ahead. And I think this is a particular I think it's quite confusing remembering it, so it's worth practicing that. But otherwise, that's that for today. I'm still waiting for 2 submission tasks from last week for a number of you, so please make sure you keep up with that. And another video from me tomorrow. Take care.